Assalamu alaikum. I welcome you to the third part of our explanation to the material, the very first material composed and delivered by engineer Dr. A.G. Ramat. We stopped here where we use ideas from Newton's second and third laws to derive the equation for the law of conservation of linear momentum. Okay, I forgot to tell you, if we have linear momentum, we also have angular momentum. Linear momentum is when an object is moving along a straight line. The momentum is regarded as linear momentum. But if an object is rotating, it has a momentum depending on the angular velocity of the object. So that momentum, we call it angular momentum. So for this particular topic, we will only consider linear momentum when an object is moving along a straight line. Okay. Here, if you look at the formula, when you clear the brackets here, when you say minus, this will come out as negative. The second term, minus times minus, will be plus. So you group together the terms with u, with initial velocity together. So it means ma sub ua plus mb sub ub on one side, and this means total momentum before collision, because u is the velocity of A before collision, u sub b is the velocity of B before collision. So MAUA, velocity of A before collision, MBUB, velocity of B before collision. Their total will be total momentum before collision. On the right hand side, you have MAVA, the momentum of A after collision, the momentum of B after collision. Okay, I am back. Now, on the right hand side, we will see that it is the total momentum of the two bodies after collision. The order of arrangement is not important. If I like, I can write this one first and say is equal to this one, or this one first and is equal to this one. Any one I write, I am correct. Okay, the next thing is an activity. This is like class activity that requires materials. Is a simple experiment, so I'm going to ignore that. Then we look at the examples. Okay, we will see how this law is used in solving problems. Example 6.8. A bullet of mass 0.05 kilogram is fired horizontally into a 10 kilogram block which is free to move. I have a bullet. This is the mass of the bullet. Then I have a block. This is the mass of the block. This bullet is fired. It hits the block, and then if both the bullet and the block move with velocity 0.5 meters per second. Okay. After the impact, find the velocity with which the bullet hits the body. Okay, meaning they want us to get the initial velocity of the bullet. Now remember, my block was at rest, so initial velocity of the block was 0, and the momentum of the block should be 0, because momentum is mass times velocity. If the velocity is 0, mass times 0 will be 0. So it means the total momentum before collision will be the momentum of the bullet only. Only the bullet has momentum. We will see that in the solution. They say let the initial velocity of the bullet be u meters per second. We don't know it, so we call it just u. Momentum before impact, meaning momentum of the bullet before impact, will be mass of the bullet times velocity of the bullet u, because we don't know it, and we ignore the momentum of the block because the block was at rest, velocity 0, 0 momentum. So this will be our total momentum before collision. Now after collision, the bullet and the block stuck together. So we have to get their total mass. 0.05 plus 10 will be 10.05. That is why they say total mass of bullet and block after collision will be this. So the total momentum after collision will be momentum after collision, the total mass times their common velocity, and we are told that after collision they move with this velocity 0.5, so we multiplied by 0.5. This will be total momentum after collision. So from conservation of linear momentum, total momentum before collision equals total momentum after collision, or you say total momentum after collision equals total momentum before collision, and that is what they did. Total momentum after collision equals total momentum before collision. From here you can divide both sides by 0.05 to get u, so your u will be this side, all of it divided by 0.05, and you will get 100.5 meters per second. You see, the law of conservation of momentum is used to solve problems. Now, example 6.9, a very interesting example. You have a body P of mass 5 kg moving with a velocity 30 meters per second collides with another body Q moving in opposite direction with a velocity of 20 meters per second. Here is the diagram. You have body P, it has mass 5 kg, it moves with this velocity 30 meters per second. You have the second mass Q, it has a mass m, which we don't know the mass, so we are not given the mass, we call it m kilogram, and it moves in the opposite direction with a velocity 20 meters per second. Now they say if both bodies now move in the direction of P at a velocity of 10 meters per second, calculate the mass of Q. Okay, meaning after collision, they all move in the direction of P, meaning this direction. So P is moving with a velocity 10 meters per second after collision. Q is also moving with a velocity 10 meters per second after collision. Okay, the question is, what is the mass of Q? Okay, to do that, remember they say we have to remember that momentum is a vector. So in calculation, we must take into consideration the directions of motion. If we take, what they are trying to say here is, if we take the velocity of P as positive, we have to take the velocity of Q as negative, because it is a vector. If one direction is positive, the opposite direction should be negative. Okay. Uh, Now they say let the mass of Q be m, so we can get the total momentum before collision. The P has a mass 5 kilogram and it moves with velocity 30, so I will multiply 5 by 30 to get the momentum of P, plus, why do I have minus? Because my 20 should be negative. Okay, this is why it changed my plus to negative. So I will now multiply 20 by the mass I don't know, the mass of Q. So 5 times 30 will give me 150, and then 20 times m will be 20m, so I'll have 150 minus 20m. I stop here. Then the total momentum after collision will be, after collision I will have to add the two masses since the velocity is the same for both. So if I add 5 plus m, I will get 5 plus m, and then multiplied by the common velocity. So 5 times 10 will be 50, and then 10 times m will be 10m. This is my momentum before after collision. This is my momentum before collision. According to the principle of conservation of momentum, this one is equal to this one. So I will equate the two here. You see, where is it here? Please come on, yeah. This is momentum before collision equals momentum after collision. I will take 50 to here and then divide both sides by 30. I will get m equals 3.33. You see, 20 plus this will be 30. So I will get m equals 3.33.